Hello friends, welcome to the video lessons on electronic measuring instruments. In this class, I am going to explain about the working principle of the PMMC instrument, then what is a DC ammeter and how its range can be extended, and what is a multi-range ammeter, then what is an alternate shunt and how a multi-range ammeter can be designed using an alternate shunt, and finally precautions to be taken while using a multi-range ammeter. As we have seen in the last class already, the basic PMMC movement works on the principle of a diagonal galvanometer, and the basic parts of a diagonal galvanometer are the coil of fine wire, permanent magnet, filament, mirror, and scale. This we have discussed in the last class. Then the PMMC movement. The construction of the PMMC movement almost will be similar to the construction of the galvanometer. This also is uh, made up of a coil to produce deflection, and it also consists of a permanent magnet and a pointer scale assembly, control springs, control weight, pole shoe, and zero position control. Why all these? The functions of all these parts in the PMMC movement are explained already. Now, coming to the working principle of the basic PMMC movement, according to the classical laws of electromagnetism, whenever a coil of fine wire is suspended freely in a magnetic field, then the coil tends to rotate. The amount of rotation of the coil depends upon the amount of current that is flowing through the coil, and the direction of rotation of the coil, of course, depends upon the direction of current flowing through the coil. Now here in the basic PMMC movement, through the control springs, the current will enter from one control spring, and through the movable coil assembly the current flows, and then through the other control spring the current will move out. Here, depending upon the direction of current, that is either it is flowing from top to bottom or from bottom to top, that is flowing in one direction or in the other direction, the coil will produce certain amount of deflection, and this deflection is responsible for the measurement, and this deflection is proportionate to the amount of current flowing, and this deflection, when observed using a pointer connected to this movable coil assembly, when observed using a pointer over a calibrated scale, can produce the visual display of the quantity being measured. Here, the scale will be calibrated in terms of the quantity being measured. As I told already, The basic parameter or the basic quantity that is responsible for the movement is current. But if we are measuring temperature, then a certain meter will be calibrated in terms of temperature. If we are measuring voltage, then the scale for the meter will be calibrated in terms of voltage. If we are measuring resistance, the scale would be calibrated in terms of resistance or any other parameter, whatever may be the parameter. The parameter that is to be measured is converted into electrical current, and that electrical current flowing through the movable coil is responsible for the deflection of the entire movable coil assembly. When the movable coil assembly produces certain amount of deflection, that deflection can be observed by using a pointer connected to the movable assembly, and this pointer will move over a calibrated scale. Often the scale will also consist of a mirror alongside the readings in order to avoid parallax error while taking the readings or while measuring the quantity being, so while taking the value of the quantity being measured. These are all the different diagrams showing the constructional details of the basic PMMC movement. And as I told already, this one would be convenient to draw in the examination, taking minimum amount of time but giving the same details of construction. And here, this is what in which we are interested. Permanent magnet is used to create a constant magnetic field. The basic PMMC movement consists of a permanent magnet. This magnet produces a strong magnetic field. And in the magnetic field, when a coil is suspended and current flows through the coil becomes an electromagnet. The coil is placed in the strong magnetic field of a permanent magnet, and in the absence of current, there won't be any deflection. The coil will be static. But when current starts flowing through the coil, it becomes electromagnet, and depending upon the direction of current, it assumes one north pole and one south pole. So depending upon the direction of current, it will produce a deflection either in the clockwise direction or in the anti-clockwise direction, depending upon the relative position of north and south poles of the permanent magnet and the electromagnet, that is the coil. The current to be measured is passed through the movable coil. The current carrying coil creates magnetic field and deflects the pointer attached to it. The deflection of the needle is proportional to the magnitude of the current flowing through the coil. This is the point of interest. The equation for torque, that is, the deflection of the pointer, depends upon the torque produced by the magnetic field. When current flows through the coil, then certain amount of torque is produced. Why? Because the coil becomes electromagnet and it tends to rotate depending upon the relative positioning of the permanent magnet poles and electromagnet poles. And the expression for the torque produced can be given as T is equal to B A I N sine theta, where T is the torque in Newton meters, B is the flux density in the air gap, Webers per meter square, A is the effective coil area, I is the current in the movable coil, N is the number of turns of the coil, and theta is the angle between the direction of magnetic field and the direction of current. Now here one point is to be noted. The magnet, a horseshoe magnet, is provided with two soft iron poles pieces. Soft iron pole pieces, here given as pole shoe. Soft iron pole pieces, and these soft iron pole pieces have curved shape. These soft iron pole pieces have curved shape. Suppose if these soft iron pole pieces are not there, let us suppose, then the magnetic field would be in a diverging fashion. It starts from one end, then from North Pole to South Pole, as we already know how the magnetic field will develop across a magnet, a permanent magnet. Now, because of this soft iron pole pieces with curved shapes, a radial magnetic field will be generated. That is important. Radial magnetic field. Radial magnetic field means from North Pole to South Pole, the magnetic lines of force or magnetic flux will be uniform, just like straight lines. Just like straight lines. Uniform magnetic field, and a radial magnetic field is generated by the soft iron pole pieces with curved faces. Now, this point, if we interpret here, theta is the angle between the direction of magnetic field and the direction of current. As you can see, the direction of magnetic field is from North Pole to South Pole, just like this. Suppose if this is North Pole and this is South Pole, it would be like straight line from North Pole to South Pole. On the other hand, the movable coil or the current, basically the direction of current is nothing but the direction of the movable coil. How the movable coil is arranged? Movable coil is arranged vertically. Here the magnetic field would be horizontal from North Pole to South Pole, and current flow through the movable coil would be from either top to bottom or from bottom to top. So in that case, the angle between the magnetic field and the direction of current would be exactly 90 degrees. When this theta is 90 degrees because of the radial magnetic field, sine theta, that is sine 90 degrees, it would be equal to 1. In that case, T can be written as BAIN. Now please observe, tau is, T is the torque that is produced B is the flux density in the air gap. For a given magnet, horseshoe magnet, the flux density will be constant. There won't be any change in the flux density. Similarly, for a given coil of the PMMC instrument, the area would be constant. Number of turns would be constant. So, the only parameter based on which the torque would change is only I, that is the current flowing through the coil. So we can say that the torque produced in a PMMC movement is directly proportional to the amount of current flowing through the coil. Now this torque in turn makes the pointer or makes the entire movable coil assembly to rotate. So along with the movable coil assembly, the pointer also rotates. When the pointer rotates, then depending upon the position of the pointer on a calibrated scale, we can tell or we can observe what is the quantity of the current that is flowing through the coil. Here, the scale would be calibrated in terms of current. If we are measuring current, the scale would be calibrated in terms of voltage if we are measuring voltage. So that is the basic principle. So the torque produced is directly proportional to current. Shows that the torque is proportional to the flux density, current, coil area and turns of wire. The basic PMMC movement of figure 2 is called d'Arsonval movement. It provides an instrument with very low power consumption and low current is required for full scale deflection, and it consists of soft iron pole pieces, and it consists of a coil which can freely rotate in the air gap, and a pointer is attached to the coil which moves over a calibrated scale. Conductive springs are used to provide calibrated counter torque. Calibrated counter torque. Suppose if springs are not there, because of the torque produced, the pointer would abruptly move from the zero position to a specific position on the scale, which may damage the mounting assembly of the PMMC instrument. So in order to avoid this, has already been explained anyhow, in order to avoid the damage of the mounting assembly of the movable coil, conductive springs with calibrated counter torque are used and current is allowed to flow through these conductive springs. And finally, balancing weight. The PMMC movement consists of a balancing weight. This balancing weight will take care of the weight imbalance on both sides of the pointer. And finally, pivot and jewel bearing. Here, as you can see, this pointed tip type pivot is used here, and a jewel bearing is used. A groove is made in the jewel with a diameter which is greater than this value. Tip size is 0.01 millimeter to 0.02 millimeter in a commercial PMMC movement, and the radius of the pit or the radius of the groove in the jewel, it has to be larger than the pivot radius. This is because suppose if the groove that is drilled in a jewel or the pit that is made in the jewel is exactly the same as the tip of the radius of the tip radius of the pivot. In that case, for every measurement, there would be some friction when the pointer is rotating. Because of that friction, the mounting assembly may get damaged. So to prevent that, the pit or groove in the jewel is drilled with slightly larger amount of dia compared with that of the pit. And another pivot and jewel bearing assembly is shown here with additional amount of weight control. Because of this arrangement, that is some spring type arrangement between the jewel and the outer body of the pivot and jewel bearing assembly, there would be a spring type mechanism. Because of this spring type mechanism, if at all by mistake the PMMC instrument is dropped from some height, then without this shock absorbing springs, there may be a disturbance in the movable coil assembly because of the disturbance in the bearing, pivot and jewel bearing assembly. But when this type of assembly is used, if at all any mechanical shock is there because of mishandling of the instrument, that mechanical shock would be absorbed by this spring, and the instrument would not get damaged by a large extent. But of course, if repeatedly the device is mishandled or used roughly, in that case, any device will get damaged. But by accident, if something happens and if the device has to encounter a mechanical shock, in that case, this type of arrangement can provide a better, what we say, a better absorption capacity to take the mechanical shock and keep the device safe. This is all about the construction and working of the basic PMMC movement. Finally, what we have to keep in mind is a basic PMMC movement makes use of a D'Arsonval galvanometer type structure consisting of a movable coil arranged in a uh, perfect manner and placed within the uh, space between pole pieces of a magnet, within the space between the pole pieces of a magnet. When current flows through the PMMC instrument, it flows through the movable coil. Movable coil produces torque, and because of the torque, the pointer deflects over the calibrated scale, giving the visual display of the quantity being measured on the calibrated scale. And as we have already seen from the equation, torque is equal to BAIN. The torque produced is directly proportional to the amount of current that is flowing through the that is flowing through the movable coil. So the pointer deflection or the measured reading is also proportional to the current flowing through the coil. So we can say that the basic PMMC movement can measure current of very low magnitude. It can be used for the measurement of current of very low magnitude. So that is all about the PMMC movement. Next, we will continue with how the PMMC movement can be used for the measurement of currents of higher values.